Good afternoon. Welcome back to ECE 207. What we are wanting to do today is first make some announcements, and then we will discuss some diode problems. I think that would be a good use of our time in this lecture to try to firm up these concepts concerning diodes relative to what we've already learned. What we need to be reminded of is that homework number 9 is due on Tuesday, the 7th of December, and our final exam is actually 2 weeks from today, and that will occur at 2 to 4 in our normal lecture room. As I mentioned before, what I want to do today is actually work some Zener or some diode problems, and in particular I've pulled out or extracted a few end of the chapter problems that I think might be helpful to your understanding of diodes and how to work with circuits containing diodes. One of those I want to look at is going to illustrate or help further illustrate the diode behavior of a Zener diode. Then we will do a load line analysis problem that actually involves or requires, doesn't require, but it's begging us to do a Thevenin equivalent, and we'll work through that load line analysis problem using Thevenin equivalent techniques. We'll then do a transfer function relationship or a wave shaping circuit. We want to see what is the output voltage V0 versus an input voltage Vn. Let's then get started with some of these problems, and in particular we will start with problem 10.7b. The circuit associated with this problem, let me sketch. It's a interconnection of several diodes, and this first branch actually has a diode and Zener diode head to head, so to speak, and then there's a second branch that really is similar, other than it's sort of an upside down version of what we just had in the previous branch. We are looking at finding this relationship between the current I that's flowing and the voltage V across this set of two terminals. We are also told that these Zener diodes have breakdown voltages of 5.1 volts and 3.3 volts. And we'll try to make it clear what that means as we go through this analysis. And what we're wanting to do then for this problem is to sketch the current I versus the voltage V in this two-terminal network. Let me try to figure out what's going on. And to help us try to better understand what is going on, let's go ahead and remind ourselves of the current voltage relationship of a regular diode and of Zener diodes. If we recall our regular diode, schematically again, that's something like this, where we have our anode and cathode being the positive and negative directions of that diode, and our current I through that diode. For that particular configuration, then we have a current voltage relationship in the forward direction. This current starts flowing rather quickly when we reach this what we will assume for our diodes the forward voltage of 0.6 volts. And that's a function or a result of the properties of the material that make up the diode, the silicon nature that's going together with the P material and the N material. That will naturally want to be forward biased or it will start turning on, so to speak, at 0.6 volts. The range of current that we're referring to usually in the forward direction is in the milliamp range. In the reverse direction, if we were to now apply a negative voltage, negative relative to how I have it labeled in the schematic here, if there's a negative voltage applied, there really won't be any current that is conducted through. So it's like a valve. It's a one-way valve until we get way out here, and then it starts to break down. And with a regular diode, this breakdown voltage, let's just say that it's out there near the hundreds of volts or minus 100 volt. And the current, my scales are not necessarily consistent in the vertical direction. The positive half are in milliamps, but down here in the negative, really in the reverse biased direction, there's very, very little current flowing, and so it's in the nanoamp region. That's what a regular diode looks like. A Zener diode has a different characteristic, not in the forward direction. The forward direction actually looks identical for the Zener diodes that we will be using in this class. We will represent a Zener diode schematically a little differently. Here's our anode, here's our cathode side, and the current I. But now, as I said, the forward current voltage relationship of a Zener diode looks the same. And what I may actually do is label, subscript some of these with the Z occasionally to try to distinguish if I am talking about Zener diodes. The Zener diode is designed to actually break down at a particular value in the reverse bias direction. And it will now break down at a designed voltage. And that designed voltage, one of the diodes in this particular problem has been designed to have a breakdown voltage of minus 3.3 volts. So I'll sketch it for that, and that now allows us, those characteristics allow us to analyze the circuit that we just sketched earlier. In the second branch, this particular voltage was 5.1 volts. The shape is going to look the same in the forward direction. It will just be different in the reverse direction. Let me now label this diagram so that we can talk about it maybe a little bit more effectively. I'm going to put a lot of different labels on this just so that we have something to refer to. Let me call this diode 1, and there is the normal voltage relationship from anode to cathode on that diode. Let me call the current through that branch I sub 1, and let me call this, or label the voltage dropped on this Zener in the normal diode direction, V sub D, Z sub 1. So I'll call that Zener diode 1. Let me say that this current is now, typically I would like to forward bias my diodes and have those functioning in the forward bias direction. This voltage drop will be for regular diode 2, and this Zener diode drop I will label from top to bottom plus to minus V sub D sub Z sub 2. That's not quite all I want to label. I actually want to label some paths that I will now use in some of the analysis. suppose that I now have a path, and I will put that in blue. I'm going to call one KVL path, and I'm using a finer pin for that. Let me call this path 1, and let me call path 2 the path that goes to the far or to the far right set of diodes. There are my two meshes or two loops that I may refer to in the subsequent analysis. What I want to do now is try to understand what's going to happen with the current flowing here relative to the voltage across that two-terminal device. If you look at that circuit, and let's just suppose, well, yeah, let's go ahead and suppose that the voltage V is positive. If the voltage is positive, that seems to indicate that we're trying to forward bias that first diode, V sub D sub 1, and if we can get that voltage drop to be bigger than or equal to 0.6, then that will be forward biased. In order to understand that, let's look at KVL around mesh 1. KVL around mesh 1 says then that we have minus V plus V sub D sub 1 minus V sub D sub Z sub 1, and that's equal to 0. Or we could solve that for V, the voltage, V, and that's going to now be equal to V sub D sub 1 minus V sub D sub Z sub 1. That might be of interest, and we want to see maybe when that's positive, or we could solve that for V sub D sub 1 and say that if we have V sub D sub 1, that's going to equal V minus V sub D sub Z sub 1. Actually, it's going to be plus that. If I now push everything on the other side, I now have V sub D sub 1 is equal to V plus V sub D sub Z sub 1. In order for that diode, first diode in the middle branch, to be forward biased, we need V sub D sub 1 to be bigger than 0.6, and the only way that's going to happen is for V to be positive. So let's see what's going to happen. And we know that if, well, let me just say we need V sub D sub 1, which is equal to V plus V sub D sub Z sub 1. We need that to be bigger than 0.6 volts in order for diode 1 to conduct. If that's bigger than 0.6 of a volt, then V plus V sub D sub Z sub 1 is bigger than 0.6, but V sub D sub Z sub 1 is like a battery when it's reverse biased. We could now say V, the only way that diode 1 is going to be conducting is if V is greater than 0.6 minus V sub D sub Z sub 1. In this particular configuration, V sub D sub Z sub 1 is wanting to be, it's reverse biased, it will start to break down at 3.3 volts, and that's the only time that current is going to flow through that particular diode in the reverse direction. And in particular, it's going to be a minus 3.3 volts in order for that to be in the reverse biased configuration. So this now says that we need V to be bigger than 0.6 minus a minus 3.3, or we need V to be 3.9 volts in order for conduction to occur. If that's the case, now then we can say that we have this voltage-current relationship. The only way that that circuit in those two terminals is going to have current flowing is when the voltage V becomes larger than this 3.9 volts. That's what's going to happen in the positive voltage direction. If V is negative, then this right-hand side is wanting to, the second diode on the right-hand side, that diode is wanting to conduct. If little v on the left is negative, that's like putting a positive voltage on the lower side of that second diode. Let's now look at KVL around mesh 2. Or we're really wanting to see when is I sub 2 going to be positive. But if we look at this KVL at 2, now we are going to see that we have minus V plus V sub D sub Z sub 2 minus V sub D sub 2 equaling 0. If we solve that for V sub D sub 2, that's going to now be minus V plus V sub D sub Z sub 2. And for this I2 to flow, we actually need V sub D sub 2 to be positive. Or for diode 2 to be turned on, we need V sub D sub 2, as we've labeled it, to be positive. That means that we need minus V plus V sub D sub Z sub 2 to be bigger than 0. But we said V was going to be negative, and that means then that we need V, if we look at this, V sub D sub Z sub 2 needs to be bigger than V. Or, and what is V sub D sub 2? V sub D sub 2, the way that we have this configured, if we're trying to make I sub 2 move through that right side or to flow, then the only way that's going to happen is if V sub D sub Z sub 2 is reverse biased enough to be in its breakdown, at its breakdown voltage, which is minus 5.1 volts. So if we say that that's what's going to happen if we want current to flow, this particular left-hand side now is going to be minus 5.1 volts. And that now needs to be bigger than V, or V needs to be less than minus 5.1 volts for diode 2 to conduct, or for I sub 2 to exist. For V to be less than minus 5.1, if we sketch that, here's our voltage, and now our current is here, but now we're saying that the only way current is going to flow is if V becomes less than this minus 5.1 volts. And we still have the forward behavior, which was this was going to allow current to flow as long as we exceeded with our voltage 3.9 volts. And this is now the answer that we need for this particular circuit. This is what the current voltage relationship will be for that particular problem, for problem 10.7 part B. Let's now look at another example problem, and this will be a load line analysis problem. In particular, it's problem P1024. And in this problem, we're told that the diode has a particular current voltage behavior given by figure P1020B. And I've actually pulled that out, and this is now the current voltage relationship of the diode that we are to examine. And in this particular case, this is a light emitting diode, and so we're trying to figure out under what conditions or at what current and voltage will this circuit actually start conducting and allowing that LED to be turned on. The circuit for this particular diode that it's connected in, and it's a light emitting diode, the circuit is now, let's sketch that. We have a 2 milliamp source which is in parallel with a 5K resistor, and subsequent to that I might actually be calling this R sub 1. So let me just label it R sub 1. Here is a voltage source, a DC voltage source of 10 volts. Here is our light emitting diode, which they now have said, okay, here's the voltage across that. Here's our current across that diode, and here is a second resistor, R sub 2, that's in parallel with that light emitting diode. And let's just emphasize the fact that that's an LED. Maybe it's a red LED with the forward voltage that we saw that it had, which was about 1.8 volts. In this particular figure or circuit, R1 and R2 are the same, and they're 5 kiloohms. And if I gave you this problem and said, okay, what will V and I be in this particular circuit, you would be trying to find the magic value or the specific value of voltage and current that satisfies this circuit, and under what condition will that LED light or be illuminated. This looks a little bit involved, but what we can do is we can redraw excuse me, this circuit. And what helps us redraw that is to notice that the diode and R sub 2 are in parallel. And because of that, electrically it doesn't matter which one's on the right side or the left side, so let's just exchange their locations schematically, and that will actually make us feel a little bit better or allow us to think through this in a more conventional way. But if we now re-sketch that circuit, and again, there's nothing wrong with redrawing a circuit. It actually maybe helps you figure out what's going on if you sketch it a little bit differently than what it was presented to you. There's R sub 2, and now let me say that what I'm really wanting to do and I haven't changed the circuit electrically at all. This is now what I have. It's the same circuit that I had before, except now I have the diode and R2 interchanged, but now I can think of everything to the left of terminals AB. Maybe I can convert those into a Thevenin equivalent, and that might allow me to more easily determine what this particular current and voltage are when that LED is placed into this particular circuit. Let's now try to find, so in this case the diode sees the same circuit. Let's now find the Thevenin equivalent between nodes A and B. One thing that you can see, hopefully, when you examine this circuit or start to think about it, there are no dependent sources. And because there are no dependent sources, we can kill these independent sources when we're trying to find the equivalent resistance looking back to the left in terminals A and B. Or we can zero those DC sources, in this case they're DC, we can zero those independent sources. And remember, zeroing a voltage source is like replacing it with a wire. Zeroing a current source is like replacing that with an open circuit. Let's now write that down. In the Thevenin equivalent, that we are trying to find, we can see that in the circuit itself there are no dependent sources. That says that we can, what some people say kill, but that just means set to 0 the independent sources to find the Thevenin resistance, or R Thevenin, if we want. And sometimes that's easier to look at a circuit that doesn't have any sources and we're just trying to find the equivalent resistance between two nodes or two terminals. Let's now re-sketch. So with our sources zeroed, what does that circuit look like? If we zero out the current source, we're now disconnecting that. Here's where our current source was, and that's what it looks like when you set it to 0. We then had that in parallel with a resistor, which was R sub 1. We now want to zero out our voltage source, and we can do that by replacing it with a wire. That was then connected to this resistor R sub 2, and then that was in parallel with our LED, which it was connected through terminals A and B. Here is our voltage source equal to 0. Now what we want to do is find what is this impedance, or in this case, since there's no frequency dependence, there's no inductor or capacitor, we're dealing with pure resistors. We're looking for the Thevenin resistance looking back into nodes A and B. hopefully it's clear by this point in the semester that the equivalent resistance, R Thevenin, is just the parallel combination of R sub 1 and R sub 2. And R sub 1 and R sub 2 were actually equal, and because of that, hopefully even now you know that that means that each of those, when put in parallel, if they're equal to begin with, just splits the impedance in half. So now we have 2.5K effectively for the resistance looking in to the left into terminals A and B. We could have computed that. Remember our parallel combination equation for two parallel resistors. That was just R1 times R2 over R1 plus R2, and that's just 5K times 5K over 5K plus 5K, or that's 25, and we actually have two K's that we have to keep track of, so that's like K, and here we have 10K. One of those K's can be eliminated. That 10 can now be put into the 25, and we're left with 2.5K for our Thevenin resistance. We now have half of our Thevenin equivalent circuit determined. Let's look at the other half, which is to find the Thevenin voltage, V Thevenin. And if you go back to the circuit, another way of thinking of that is, what's the open circuit voltage, V open circuit, at terminals A and B? Again, we're removing the diode and we're trying to find what does the open circuit voltage look like across terminals A and B. Again, let's resketch the circuit. We have to keep our sources in now if we're wanting to find the Thevenin voltage. Here's R1, here's our battery, which was 10 volts with the appropriate polarity. And there's our terminals A and B, and we are trying to find that voltage VOC. What's a process that you might have in trying to find that? Well, I would say, you know what, if I knew this current, let me call it I sub 1, down through the R sub 2, then I would know what V sub OC was. I know VOC is now R2 times I1. But now you're saying, well, what is I1? Well, can we find that in any way? And now, if somebody's wanting I1, I know this voltage, this current. I know this current, so that's the current coming here to the right. If I only knew this current, then I could find I sub 1. Let me call that I sub 2. Or now I'm really asking, what is this KCL relationship at node 1? KCL at 1 says the current coming in, which is 2 milliamps, must equal the current leaving, which is I sub 2 plus I sub 1. Alright, so now I know what the relationship is that I need, but now what is I sub 2 and I sub 1? Well, if I knew this voltage, let me call it V1 since I've labeled that node 1, if I knew V1, I could find I sub 2. Well, let me see if I can find I sub 2, or I'm sorry, V sub 1. What is V sub 1? Or can we find it? And we can use this KCL equation to help us figure out what V1 is. We have that various pieces. We don't need the left side, we already know that, but I sub 2 is just V1 over R1, or did I label those differently? That's R1. Then I know that, well, do I know? So that, I know R1, I don't know V1. Hopefully I can now re-express this KCL equation in terms of the one unknown, V sub 1. What's I1? And in particular, can I actually find that in terms of this unknown node voltage V1? If I go back to my circuit that I was last looking at, hopefully it's clear that maybe if I were to do a KVL, and now what is V1? V1 is just this voltage drop right there from this reference node, which is the bottom terminal, up to that node on top of R sub 1. That's just node 1. Let me now do a KVL equation around there. Let's say that that's mesh 2 or loop 2. In terms of loop 2, I can now write the following. I can say minus V1 minus 10, I'm entering the negative terminal of that 10-volt battery, plus, and now what was over on the right-hand side? Was that R sub 2 times I1? Maybe I shouldn't have labeled that R sub 2 and I1, but that's now R sub 2 and I sub 1. That's brought me back to where I began, and so that's my KVL equation that I was after. And now it looks like I know R sub 2. I can find an equation for I1 in terms of V1. And that's what I was looking for. R2 I1 is now V1 plus 10. Or I1 is now V1 plus 10 over R sub 2. Now I can use that I1 expression and the I2 expression in my KCL equation that I had at node 1, which was this 2 milliamps, equaling I2, which was V1 over, whoops, labeled that R1, didn't I? R1 plus I1, which is V1 plus 10 over R2. And remember, R sub 1 and R sub 2 were the same, and they were equal to 5K. Let's multiply both sides through by that 5K amount to clean things up, and we now have 5K times 2 milliamps is equal to V1 plus V1 plus 10. The K and the milli cancel, and I'm then left with 10 is equal to V1 plus V1 plus 10. The 10s cancel, and now I have 0 is equal to 2V1. What's going on here? V1 is equal to 0. Does that make sense? Do you now start going back and trying to rework the problem? Well, let's just hold on. Let's try to figure out if that's actually okay. If this result. Let's see if this is okay. That's not a question, that's an exclamation point for that one. So let's see if that's actually acceptable to have V1 equal to 0. We still have our I1 equation. I1 from before was equal to V1 plus 10 over R sub 2. And we just computed this to be 0, but that's okay. We now have I1 is 10 over R2. R2 was 5K, or this is now 2 milliamps. And remember what we were after, actually. We were after this open circuit voltage, which was this R2 times I1. R2 was 5K. I1 we just now found to be 2 milliamps. Or that says now that the V open circuit is 10 volts. We now have our Thevenin equivalent. That's hopefully going to allow us to solve this load line analysis problem. Here are terminals A and B. Here's our R Thevenin, which was the 2.5K. Here was our V Thevenin, which was 10 volts, and that is now connected to this light emitting diode, and we're trying to find V and I for that circuit. And remember, the diode actually behaves like this particular, or has this particular current voltage characteristic. And now what we can do is use this circuit to find the load line. In doing that, if we write KVL in this circuit, hopefully now it's clear that that's minus 10 plus R Thevenin I plus V is equal to 0. And that's our equation that we need, or we now have a linear equation. We can plug in a couple, or a value for current and a value for voltage, and try to find the respective voltage and current values and sketch our straight line with that information. Let's suppose that we look at V equaling 0. So what's the current on our vertical axis when V is equal to 0? If we plug V equal to 0 into this equation, we then end up with I equaling 10 over R Thevenin, that R Thevenin was just 2.5K, or this now becomes 4 milliamps. There's one of our points on our plot. What if we now say, okay, what's V when I is equal to 0? If I is equal to 0, the R Thevenin I goes away, and we see that V is equal to 10. If we go back to this circuit, well, 10's not even on my horizontal axis. I basically stop at 5, so maybe that wasn't such a effective value to use with I equal to 0. Why don't I just say, you know what, I found a V equals 0, why don't I just look at a different voltage, and in particular, what if I look at V equal 5? Since this one right here, that point was off the graph, and I don't want to try to extrapolate and figure out where 10 is. I want to play on the graph. So at V equal to 5, we end up with minus 10 plus 2.5K, that's R Thevenin, times I, plus 5 equal to 0. If I now solve that for I is now 10 minus 5 divided by 2.5K, or it's 5 over 2.5K, or it's 2 milliamp. that now hopefully allows me to find a point that's going to maybe be a little easier to locate on my graph. If I now look at trying to intersect those 2 points, I started with a voltage of 0 and a current of 4, and now I want to connect that point with a straight line to this point that is at V equal 5 and 2 milliamps, and that's now my load line associated with that Thevenin equivalent circuit. I now have determined what my current voltage relationship needs to be if I wanted to try to get that a little bit more accurate. I'm not sure that I'm going to be able to do it that cleanly here. That looks like I'm a little bit to the left of where I needed to be, but that's getting me in the ballpark. I now have a point. Whoops. It's not what I wanted to do. I wanted to draw a straight line. And hopefully from there it's clear that our current is roughly 3.25 and our voltage is about 1.8 volts, and that's now the intersection of those two lines that are supposed to simultaneously be satisfied for this diode circuit to operate. So we went to our figure, which was P10. I've forgotten what the figure was for the diode. I think it was figure P1020B. We were able to find this intersecting point, and that ended up being a current equal to 3.25 milliamps and a voltage of 1.8, the book maybe says 5, but 1.85 milliamps. And we were able to find that by first doing a Thevenin equivalent and then doing the load line analysis. Let's now look at a wave shaping circuit. Type problem, and in particular we're wanting to know what does the transfer characteristic of a particular circuit look like. Or in other words, if somebody gives me an input voltage applied to a circuit, what's the output voltage, and how does the output voltage relate to the input voltage? What's my graph relating VO to VN? To examine that for a particular circuit, let's look at problem 67 in chapter 10. With this particular problem, they want us to find the output voltage V0 versus the input voltage Vn. Here is our schematic. We have our input voltage, which can be adjusted. It's variable. and they're telling us what particular range to allow that to vary through. We then have a 1.2 k ohm resistor. We have our diode, and we have then a couple more resistors. Here's a 2k resistor, here's a 3k resistor, and here is a battery, 5 volts. And finally, here is our output voltage, V0, that we're after or interested in determining. What does that output voltage, V0, look like for different values of Vn? And in particular, they tell us, go ahead and let Vn range between minus 5 volts and plus 5 volts. And what we're wanting to do is we want to find a relationship relating the output voltage V0 and the input voltage Vn in this particular circuit. And let's just look at this for a little bit, and really what do we have? We can think of this as, alright, what are some possibilities? Well, this particular diode could be on or it could be off, and in the various configurations, let's just analyze what's happening. Meaning, if the diode is off, what's going to happen? We now have an open circuit right there. If that's now an open circuit, then we really are just connecting this Vin to Vout, and there's no current flowing across or through that top branch if VO is an open circuit or no load on it. So we now have diode is in one of two states. It's either off or on. So let's now just look at this circuit under those two conditions. Let's look at when the diode is off. If the diode is off, what we have is then a circuit it really doesn't matter necessarily what's going on here at this point, but it will determine when we are off and on. But for now, we're just assuming that it's off. Here is our V sub D. This was 1.2K, and here is our V0. And this might be our current I, and this is our input voltage Vn. With the diode off, we can now look at this particular KVL equation and see that we have minus Vn plus 1.2K times I plus V0 is equal to 0. If we do not have anything connected to V0, there is no current flowing, and because of that, then V0, or the output voltage, is simply equal to the input voltage when the diode is off. So now that that diode is off, when is that diode off? That diode is going to be off as long as this particular voltage, let's say at node 2, as long as that voltage is more positive than this voltage. That's the lower node. So now diode is off. When V sub D is less than 0 for an ideal diode. And what is V sub D? Well, if we look at that, we can now say that if we called this voltage 2, and maybe this is now voltage 1, we can say that if we did a KVL around there, we would have minus V sub 2 plus V sub D plus V sub 1 is equal to 0, or V sub D is equal to V sub 2 minus V1. And we want that now. We're interested in when is that going to be less than 0 or bigger than 0. We want to know when does that transition for an ideal diode. So we now have this V sub D is equal to V sub 2 minus V1, and for now we said when is it going to be less than 0? Well, what is V1? And can we find it? So if we go back to this circuit, hopefully it's clear with that diode off what V1 is actually equal to. V1 can be found from a voltage divider. This was 2K and this resistor was 3K. We have 5 volts dropped across a total of 5 K ohms, and V1 is just that voltage associated with the drop across 2K of that total 5K. Or from a voltage divider, we can say that V1 is actually equal to 2K over 2K plus 3K times 5. Or you could just write a KVL equation around that, and now you see that V1 is actually going to be 2/5 of 5, or V1 is now 2 volts. As long as, what does this say? This now says that we want V2 minus V1 less than 0, or we need V2 less than V1. As long as V2 is less than, and what is V2? V2 is actually in this circuit without any current flowing. V2 is Vn. So now we know that as long as V2 in this case, which is Vn when the diode is off, as long as that's less than 2 volts, then we know that V out is equal to V in. Now, what happens when the diode, or when this condition is not true? So when V2 is greater than 0, I'm sorry, when V2 is greater than 2, then the diode is going to be on. So let's now figure out the circuit, or re-sketch the circuit when the diode is on, or when that current I sub D is actually flowing. So with the diode on, let's re-sketch the circuit. Again, we're just looking at this circuit under 2 possible states. One state is when the diode, and we're treating this as an ideal diode, when the diode is off. We just analyzed that. Now we're going to put that diode on. Now that it's on, it's just acting like a short, and there is the 2K resistor, and that's also connected to this 3K, which is now connected to this 5-volt source, and all of those are then connected to V0. If this is our circuit, this looks very similar to what we've already analyzed all semester. Now V0 is this voltage, or that node voltage, that's V0, and let's now solve for it, and we can do that if we look at or find or write the KCL equation for that particular node. We have I1, we have I sub 2, we have I sub 3. There's no current going to the right because that's an open circuit. We now can say, okay, KCL at that top node says that we now have V0 minus Vn over 1.2K plus I sub 2, which is V0 over 2K, plus I sub 3, which is V0 minus 5 over 3K. Those currents need to sum to 0. That we were just saying was I1 plus I2 plus I3 is equal to 0. Let's clean that up a little bit. We have a common multiplier downstairs. If we just take all of the denominator pieces, obviously it's scaled by k, but now we have 6 times 1.2, or 7.2k. If we multiply both sides through by that, then we will end up with 7.2 times, or divided by 1.2 gives us 6, so we have 6 times V0 minus Vn plus 7.2 divided by 2 is 3.6, so we have 3.6 V0, and finally we have 7.2 divided by 3, which is just 2 times 1.2, or 2.4, times V0 minus 5. All of that is equal to 0. We haven't changed this relationship between Vn and Vout. We just said, okay, if the diode is conducting, this is the configuration that we have, and we want to find this equation that relates Vout and Vn. Let's now collect our terms that are in common, or keep all the V0 terms on the left. We now have 6 plus 3.6 plus 2.4 times V0. Move our other terms to the right, and we have 6 times Vn and 2.4 times 5. What's in parentheses are the coefficients scaling V0. If you add those up, that's going to be 12. V0 is equal to 6 Vn, and 2.4 times 5, we have 10 plus 2, or 12. We now divide everything by 12. We have the equation that we wanted. We have V0 is equal to 1/2 Vn plus 1. And that's now our relationship relating Vn and Vout when this diode is on, and that's going to be true when Vn was bigger than 2. Now we have enough information to actually sketch our relationship between Vn and Vout. Vout, if we remember, I may have run out of room, but V out was equal to Vn as long as Vn was less than 2. And when it was less than 2, V out was equal to Vn. So here's minus 1, minus 1, here's minus 2, and we can just take that all the way down to 5. In this particular case, we are going up 1 and over 1, so our slope is 1. Vn is equal to V out. Whoops, V out is equal to Vn. After that, when the diode kicks on, then we have a slightly different relationship. And let's just verify that that is still true at this transition point at 2, 2. When Vn is equal to 2, we get V out is equal to 2, so it looks like we're okay right there. What about, or what do we do now? Well, now we're having a slope of 1/2 beyond this point of 2. Or if we go up 1, we have to go over 4 for that same change. And hopefully that indicates a little bit of a slope change. This is now, we're going up 1 and over 2 for our slope beyond this particular transition location or point, which was the point 2, 2. And that's really the transfer function relationship that we're wanting in this particular problem, is we're trying to now find or determine in this circuit how does our output voltage behave, or how is it shaped by the, or how does it shape the input voltage. And it now says, well, it's going to be an exact copy of the input voltage up until we get an input voltage of 2. Again, this was for an ideal diode. And then beyond that, it's going to have a slope of 1/2. And we were able to determine this transition or this behavior by simply looking at the diode in one of its 2 possible states. We looked at the circuit when the diode was off and determined under what conditions that was true. Then we analyzed V out versus Vn. Then we said, well, what happens when the diode is on, and when does that happen, or under what conditions is that true? We allowed the diode to turn on. For an ideal diode, the diode is replaced by a wire or a short. We looked at what would happen, and we found that our output voltage and input voltage relationship for that particular circuit, and that allowed us to then determine this overall transfer function characteristic. I think that's probably enough for today. We went through 3 problems for the diode, and they all were interesting problems, and I hope that that helps you now be a little bit more comfortable with working these diode problems.